Sorry.
So now we have our principal lecturer, Anna Mazzucato, who is going to give her first lecture. We're looking forward to it.
Thank you so much. First of all, it's really an honor and a pleasure to be here. I would like to thank Zachary and Irma for all the work that they put into this, and the university, of course. So my talks will be a little bit more pedagogical in nature. So there are students in the audience and maybe people that are not exactly in this area. So for the expert in the area, you can safely to sleep or what? But okay, and I'd like to acknowledge the support of the National Science Foundation. So my slides are handwritten, but hopefully they so I will go very slowly through them, so there will be time to actually read what there is. And let me just say that my working mixing was very much inspired by Charlie Bird, that was already mentioned by Wei, and unfortunately he died prematurely in 2021. So I would like to devote these lectures to him. And this picture is a famous picture because he was an avid football fan of college football, and he had the entire outfit made with the colors of Michigan, University of Michigan. So that's how he would go to the football game. Okay, so I wanted to spend a little bit of time introducing the problem, motivated it. So we are interested in studying passive mixing in the context of passive scalar equations. So think of course, for example, dyeing water, but even quantities that in principle are active mixer, that is a feedback of the scalar onto the flow can be under some condition considered passive, for example, temperature in oceans and the atmosphere. And all I say will be in the context of incompressible fluid mechanics. So the velocity field will be divergence free, and the volume will be preserved. So this is an important problem, on one hand analytically, because it brings in interesting ideas and interesting problems for many different areas. For example, related to regular transport, which will be important part of my talks. But also when you combine fusion and mixing, that leads to concepts that will be explored by other speakers, such as enhanced dissipation and anomalous dissipation. So there is a connection with turbulence here. So in fact, there is an entire theory of so-called scalar turbulence in the context of passive mixing. Of course, it's an important problem in application, as well I already mentioned. In particular, for example, to study how pollutants are dispersed and in the geophysical context, but of course also in industry, because when you want to make new material, most of the time you start with some kind of fluids and you mix them, different type of fluids, and you mix them. It was already recognized relatively, late, that is in the 40s and 50s. There are two main mechanisms for mixing. On one hand, you have the action of the flow alone, the storing by the flow, and you can see that as a filamentation. There was some beautiful picture in the talk by Wei as filamentation of the tracer field. So growth of derivatives, and this idea of growth of derivatives will reappear several times in my lectures. But of course, there's also mixing due to diffusion. And for now, well, for most of my talks, not all of my talks, I will neglect the diffusion. This will be discussed by other speakers. So I will primarily concentrate on the effect of storing. I will also neglect, this is an important problem in practice, but just to make things as clear as possible, I will neglect the presence of sources and sinks. So here's a couple of pictures to show you really how mixing is fundamentally in the geophysical context. They are taken by this very beautiful site called Visible Earth by NASA, so it's a collection of publicly available pictures. These are both satellite pictures, I think both of them in full color. And the picture on the left is global CO2 concentration in 2013. That apparently was a record year. It was the year with the highest CO2 concentration. Dark spots are low CO2 concentration, and the white spots are high CO2 concentration. So you see, of course, over the northern hemisphere there is more CO2, and it's important to figure out whether there is a way to kind of make things less white, purple, but more like in between. And mixing is really very important process in the ocean. In the picture on the right, you see active mixing. So you see different colors. That's due to, and also the presence of swirling in the ocean, due here to the presence of islands. The islands act as the obstacle, and that induces mixing. So we would like to study these problems in a little bit more quantitative way. And of course, there is a gigantic literature on mixing because it's a very important problem and a problem that has many facets. I would like just to mention some context in which it arises and some names of people that are work, so I cannot mention them all. So there is an important connection to turbulence, which I already made. But of course, mixing has been studied for ages in the dynamical system. In the dynamical system community, in particular, in the context that I will discuss, there's work of Aref, Ivarani, Utino, some of my former colleagues, local Piat. You can approach the problem as a homogenization or singular perturbation type of approach. We saw in the work of Wei an optimal control. Also within the context of incompressible fluid mechanics, there are connections with some things that have had important development, especially recently. So when you put in back dissipation, there is this idea of relaxation or dissipation enhancing flows that will be discussed in other talks. And I want to mention here particularly the work of Peter Constantine and collaborators. And there's also a connection with so-called implicit damping and stability for Euler flows, in particular the work of Jacob Pedrossi and Adriano Smuldi, Michele Conti-Zelati, and collaborators. The approach that I will take here is based really on combining PD's tool with geometric tools. So there will be pictures, many pictures throughout the task, because we really use in many different results a geometric approach. And by geometry here, I mean two things. On one hand, really classical geometry, and on the other one, geometric analysis, geometric measure theory, in fact. So we want, so you see there's a connection with many different areas. And first of all, the way that we study mixing is related to, or that we will create mixing in some sense is due to irregular transport. So I want to spend a little bit of time for the student to talk about irregular transport. So what do I mean by that? Okay, so from the point of view of the PDE is in some sense the simplest PD possible that you can write down. It's a linear transport equation. So convective derivative of theta equal to 0 within the initial conditions. So I will refer to that as T, equation T for transport. So U here is a given vector field. And I will work mostly on the torus, in fact, on the two-dimensional torus, but in some situation, I'm also working the whole space. So U is a given divergence-free vector field, and theta is a scalar field, which represents your tracer. Now, we will mostly assume that you don't solve equation P in a classical sense. In other words, U as limited regularity, which will be encoded as a certain Sobolev regularity. However, even when U is regular, the reason why mixing is complex is because from the point of view of the flow view, the dependence on theta on the flow is nonlinear. So the PD is linear, but from the Lagrangian point of view, the dependence is nonlinear. So that's what creates the complicated patterns that you see in mixing. And I would also like to point out that because at least formally, the transfer equations are fully true if U is very regular, so the transfer equation is equivalent to the continuity equation. And so for most of the lectures, I will just work with periodic boundary condition because I wanted to study mixing in the bulk of the fluids. In the Charcoal way, it was already pointed out that in fact what happens near the boundary is important, but we have to start with just understanding what happens in the bulk. So we work with periodic boundary condition. And the first non-trivial dimensions is this divergent free that you can take is 2. And although this makes the analysis from the point of view PDE and analysis easier because you are into dimension, from the point of view of the mixing is in fact the most constrained dimension. So in some sense, you expect things will be better if you go to higher dimension because you have more direction in where to mix. So for that reason, actually taking two dimension is appropriate. So I will refer to U here in the transfer equation as the advective velocity. When I talked about advective velocity, I mean this U. So let's review for the students mostly what happens if you're regular. And here the discriminant is Lipschitz regularity. So if your velocity field is uniformly Lipschitz, uniformly in time and Lipschitz in space, then you have the classical Cauchy-Lipschitz theory. And so you can solve the transfer equation just by the method of characteristics. So what does that mean? So what does that mean is that, first of all, even if U is regular, you can think of solving this equation here in a weak sense if theta 0 is not very regular. For example, theta 0 is just an essentially bounded function, then you're not solving this equation in classical sense. So you're looking for a weak solution. So weak solution simply means that you will test the equation with some appropriate test function and move the derivative, which will not be defined in a classical sense of the test function. So, but if U is Lipschitz, you still have some nice things even for weak solution, because the weak solution, starting with initial data which is in LP, most of the time I would assume that theta naught is bounded, so P is infinity. But in principle, you could take theta to be in any LP, 1 to infinity. It's a Lagrangian solution. So what do I mean? I mean that theta at point x and time t, and if this is essentially bounded, this will be just almost everywhere. It's exactly obtained by taking the initial condition and apply to it the inverse of the flow map. So I will denote the flow map by capital phi. So the flow map, if U is regular, is the solution of this system of ODEs. Now U will not, so we're not in the autonomous case, so U depends on time, not just to the flow, but depend on time to just the definition of U. So for most of my lectures, U will not be an autonomous system. And okay, so the solution of this system over this is called the flow, and then we take the inverse of the flow, apply to the initial condition, and that will be our solution. So you're saying that the solution is constant along the flow lines, along the integral course of the vector field. Sometimes in fluids, this inverse of the flow is referred to the back to labels map because, of course, you can think of this X as being an initial label for your particles, right? So your particles around by the flow, you label them. That's this phi inverse will tell you which label you came from. And And so if U is Lipschitz, then the flow of U phi is also Lipschitz space. And you have this bound of the Lipschitz norm. So the Lipschitz norm of the flow is not conserved. It can grow exponentially fast. But okay, you have a control time of the Lipschitz constant. Furthermore, the weak solution is unique. And if theta naught is Lipschitz continuous, then theta is also Lipschitz continuous. So this is a really nice and well-posed theory, but the moment that you go to lower regularity, you go from Lipschitz to Sobolev, then most of this breaks down. Not entirely, but most of it. So what about if we have Sobolev velocity? Now I assume that U is in L infinity in time, but with values in W1P. So what W1P is an LP-based Sobolev space. So I will most of the time only deal with LP-based Sobolev spaces with integer regularity. So they are easy to define. WKP is the space functioning LP, such that all the derivative up to order K, weak derivative are also in LP. And then the Lipschitz space correspond to just taking the now, first of all, you may ask whether the equation still makes sense, at least in a weak sense. So I move all the derivative onto the test function, and the answer is yes, but you have to make sense. So remember, U is divergence free, right? So this equation is equivalent to this one and is formally. So if you're thinking that, you know, the weakest setting in which I can solve this equation is distributions, then U times theta has to be distribution. So if theta is in LP, U better be locally in LP. Okay, so I mean the torus or local just means, I mean LQ. So I have to assume that, you know, this product is, it's a well-defined as a function in L1. So if U is in LQ, okay, then I can still write down the weak formulation. So weak solution will exist, but they may not be unique. I noticed that if P is large enough by the Sobolev embedding, then this condition that I'm in LQ will be satisfied. So in some sense, in my lectures, I will not worry too much about the fact that there has to be equality between U and Q, because U will be in most LP spaces, and also because I will take theta to be bound. So okay, you have the existence of the solution, but you don't have uniqueness. So okay, this for example, if you want to mix in a certain way, that could be a problem. So can we restore uniqueness for this solution? And the answer is yes, but you have to look for weak solutions that have additional properties. These are called renormalized solutions. And they go back to results of Ron Perna and Leon in the 80s. And the idea of renormalized solution, I don't want to write down the precise definition, but I will say the following, that informally, theta weak solution is a renormalized solution. If you regularize the equation by applying a suitable function to theta, then you still have a weak solution. So in other words, if I take beta of theta, where beta is a continuous function, so think that you are truncating theta, because theta could be very large at some point, so you are truncating by applying a smooth truncation or continuous truncation, then things are still good. You're still solving the equation, the transfer equation. That's what the renormalized solution is. And it turns out that renormalized solutions are unique. Now, let me say that very recently, I think it was 2021, I think, there is work of Laszlo Cecchilidi and Stefano Modena where they looked at weak solution of the transport equation. There are no renormalized solution, in particular because this duality condition here, the 1 over b plus 1 over q should be equal to 1, is not satisfied. What they showed is that in some ranges where this condition is not satisfied, in fact, you don't have uniqueness of weak solution in a very dramatic way. So in other words, you can construct infinitely many solutions by these recent techniques of convex integration. But for us, on the other hand, none of this will happen because we will always work in the context, except in one case, in the context of renormalized solutions. So you should think that there's still workloadness, maybe not in the sense of continuous dependence of the data, but on the sense of existence and uniqueness of weak solutions. On the other hand, from the point of view of the flow, if the velocity is Sobolev, well, in which sense the flow exists, the best you can hope for is that the flow exists in almost everywhere sense. So, let's spend a little bit of time discussing properties of renormalized solution. So, one way that you can try to construct is by regularizing the problem. And it turns out here that the way that you regularize the equation matters. In principle, if you regularize by modification or by so-called vanishing viscosity, which simply means that you add a little bit of a Laplacian to the equation and you with the coefficient and set it to 0, in principle, these two are not equivalent. And until very recently, that is in the work of Gianluca Crippa and Stefano Spirito, and there's also some further works after that, it wasn't known whether if you use in all cases, whether you regularize by modification or vanishing viscosity, whether you get a renormalized solution, which will be unique. So you can push to the unique solution in that case. But now it is known, so if you take theta in LP for any LP, even equal to 1, under some conditions, then it doesn't matter if you regularize by modification of vanishing viscosity, you converge to the unique solution. And one of the most important properties of renormalized solution is that the LP norm of theta are, in fact, in some sense, any function of theta are conserved, because that's how you define the renormalized solution. So, so for us, we will use the fact that, particularly L2 norm of theta, it's exactly conserved. And another important aspect, or one example which I will present, is what if you go a little bit further to less regular vector field? How far can you push this theory? And the natural extension, since you go all the way to W11 in the Di-Parnalion theory, is to say, well, can you take BV function? So BV means bounded variation function. So think of taking the weak closure of W11. So the derivative in W11, the gradient is an L1 function. Can I make it a measure? Okay. And the answer is yes. This is a really non-trivial extension of the Di-Parnalion's theory due to Giambrosio. And you can extend the theory of renormalized solution. In particular, you still have uniqueness if U is integrable in time with values in BB. So keep this in mind, because I will give an example later on. It's a very simple example of a mixing flow for which you don't have uniqueness and the velocity is exactly on the line. So you cannot do better. This is sharp. Okay. And why is BV important for application? Because BV allows sharp interfaces, right? So the example that I will present, in fact, is really sharp interfaces. You can start to understand that if I allow sharp interfaces, then it would be easier to than if sharp interfaces are not allowed. So really there will be a dichotomy in some sense when you go from controlling derivative in LP to controlling derivative as measures. Okay, so this was already a little bit discussed by Wei, but let me go through this again just to formalize things a little bit. So we want to really be very quantitative. So we want measures of mixing that that allow us to do analysis. So it's easy to say formally what does it mean for scalar theta to be perfectly mixed, because okay, you can say, well, theta will be perfectly mixed is equal its average. But it's not that straightforward to devise way to quantify how you approach this average value. And throughout, I will always assume that the average actually is zero. So I will subtract the constant, the average. This is the average is preserved in time in for good solutions. So throughout all of my my initial condition will be mean-free. And then, of course, we will say that theta is perfectly mixed if theta converges to zero. However, notice that it cannot possibly be strong convergence, because I just showed in the previous slide that if you are in the context of renormalized solution, the autonomy is conserved, right? So unless you start out with theta equals zero, then nothing happens. You cannot have strong convergence here. So the convergence of theta to zero can only be in the weak sense. And I will take it to be weakly in L2. And the time at which this weak convergence happens, I will call it the mixing time, could be finite or infinite. I will give you examples of both. And there is, in fact, a direct connection with the idea of ergodic mixing in the ergodic sense, strong mixing. So you're going to say that the flow is strongly mixing if the following happens. If you take two Borel measurable set, A and B, with positive measure, then you're looking at B intersected with the images at discrete time under the flow of the first set. Okay, so this is just the push forward of the flow, so the image, okay, of the set A under the flow. And you see what you want to see the correlations, okay? So the measure of the intersection as n goes to infinity will converge to the product of the measure. So you have completely decorrelated the two fields, okay? So I will try to be consistent and hold little lambda at that measure. So you can start to see that there is a direct connection between these two, even if theta is a function and not the characteristic function here, because you can approximate any measurable function, any function in NP with simple functions. Okay. And again, as I said, this condition says that theta zero, if you read it in terms of the solution of the transport equation, theta zero and theta time t are completely decorrelated when you take theta zero to be the characteristic function of a measurable set. But by using the fact that simple function are dense, in fact, you can see that if you have ergodic mixing, you would have perfect mixing in the way that I introduced. So the two things are equivalent. Now there are two fundamental questions now that we have this formal definition. Well, if you do, if you have mixing, at which rate you mix? So in other words, depending on the regularity of view, what is the optimal mixing rate? And then, of course, given the regularity of view, are you mixing perfectly in finite time or infinite time? And in order to answer these two questions, we wanted to introduce this quantitative measure. And one way that this is done is through, as we already mentioned, is the use of negative subalternative norms. So for convenience, I will just use L2 based norm. And then I can define them using Fourier series among the torques, okay? So I will define the Fourier coefficient even for distribution in the usual way. So testing again plane wave here. And then I can define this HS norm now for S any real number, not just an integer, be positive, could be negative, just by this quantity here. Okay, so I take the Fourier coefficients and multiply by this three factor, this multiplier, and then I take the L2 norm. So that will be my definition of the HS norm. So notice that I've taken a k different than 0 here because S could be positive or negative. So technically these are the homogeneous Sobolev norm. But because I always take mean-free initial data and hence mean-free solutions, the two norms are equivalent. So I should put a dot here, but in fact the dot norm and the regular norms are equivalent. So I will go back and forth with the two. And okay, so this will be my definition. And why is it that negative Sobolev norms can help to quantify mixing? We will collectively call them mixed norms. Well, you can see just by rescaling. Okay, so if you rescale F, it's easy to see that something very specific will happen to the HS norm. And if S is negative, okay, if you rescale going from scale of order 1 to small scales, you will make the negative Sobolev norm smaller, okay? So in other words, the S norm for S negative amplifies large scale and penalizes small scales. So if you're mixing, you are creating small scale. So you're moving energy from large scale to small scale, scale of order 1 to small scale. So what should happen with the negative Sobolev norm is that they should go down in size. So if you're mixing, the negative Sobolev norm should decay in time. And in fact, it's a simple lemma. This was in the work of Charlie Dorian and Jean-Luc before, but in fact, this is known before in some sense. It's a simple lemma that says the following, that if you take a sequence of function in L2 of the torus, true in any dimension, but as I said, I work in the two-dimensional torus with a zero average, then the time goes to 0 weakly in L2 if and only if all the Sobolev norms go to 0. Okay, so I can take any negative Sobolev norm I want to quantify what's happening on this side. So in 2D, what happens is if you normalize the L2 norm of the tracer, remember this is constant in time. Okay, so let's say that we start out with the L2 norm equal to 1. Then, in fact, the -1 norm is the dimension of a length scale. So it's convenient to use the -1 norm because the -1 norm then can be identified as the characteristic scale of the tracer field. Sometimes this is called the mixing scale. And so that's what we will use. Okay, so we will use the -1 and negative Sobolev. And in fact, for reason that will be clear in the next slides, I will call them the functional mixing scale, yeah, because it's defined using a norm, a Sobolev. There will be also a geometric definition in the next slide. Okay, so as was mentioned already, other mixed norms used in the literature. In fact, in the work of Mathis, Metzik, and Petzold, they use the -1 norm because, as you saw from the definition that we gave, okay, there is a more direct connection of that for trying to estimate the correlation with the tracer. So they use the -1 norm, but we will use the -1. Sorry, they use the -1/2 norm, we will use the -1. Now there is a related geometric concept, which is really in some sense the characteristic length scale of the tracer. And this concept is related to the idea of epsilon mixing and the idea of the cost to rearrange a set. And I want to introduce this because it's really what you need to study the mixing rate here. So let me explain this. So this idea of epsilon mixing and rearrangement cost, in fact, was introduced by my colleague Alberto Bressan, and there is a conjecture which I will remind on the cost of rearranging sets. So let me start with the definition of epsilon mixing. So you take a measurable set and you want it to control its size. So let's say that it's half the measure of it is half the measure of the torus. And you're going to say that these kappa mixed to scale epsilon. So epsilon will be a positive number. Of course, you should think small, okay, less or more than 1, and eventually very small. And kappa is a parameter between 0 and 1/2, which tells you, which controls this mixing in terms of fraction of the torus. So you're going to say that the set is kappa mixed to scale epsilon if for any x on the torus, the measure of the intersection of the set A with a disk of size epsilon at x is basically comparable to the size of. So in other words, if you think of A as being black and the rest of the torus is being white, you go down with the microscope at scale epsilon, and you still see roughly 1/2 portion of black and white up to this fraction kappa. So I have a picture in the next slides. So how do you relate this idea of epsilon mixing for set to the mixing that I described before? Well, we want to apply this notion to the level sets of the function. And this in particular, it's clear if it as a binary function. That is, it takes values +1 and -1. So it's 1 on a certain subset of the torus, -1 on the complement. And now if we're thinking of this context, we take the +1 set to have half the size of the torus. And then we evolve this set in time, pushing it forward by the flow of it. Okay? So then we can give a geometric version of the mixing scale. We're going to call it the geometric mixing scale at time G. This will be the smallest scale epsilon at which the epsilon mixing holds for the set A equal A of T. That is the push forward of the level sets of theta. Okay. So this is so the picture here is this. You have you start out with a tracer field that look like this. Say +1 here, -1 here, or vice versa. You evolve it, sorry, it's a psi phi, you evolve it with the flow of U, and you're gonna have some complicated patterns here. And you, for each point x, you zoom down to a disk of size epsilon, and you want to see on average the same as fraction, not pattern, but the same fraction as you start with that. Now, epsilon G and epsilon F are not equivalent. In my work with George Lin, Evelyn Lumazin, Alexei Novikov, and Charlie in 2012, where we studied some of this, we looked at the relationship between epsilon G and epsilon F, and they're not equivalent. So you can construct an example where epsilon G will be of order some epsilon to some power, and epsilon F will be of order epsilon to a different power. Okay, so they're not equivalent. However, you can show that they decay, both of them. So if one decay, the other one will decay, and they decay at similar rates up to constants. So particularly, both of them will be 0 at quantity mix. So I will kind of switch back and forth between the two of them for that reason. Let me also point out that I said we want quantitative estimate, but in fact, I was cheating a little bit because by quantitative, I mean the rate is quantitative, but the constants, we will not track down. And the constants are in some sense very important in practice, but it's very difficult to track the constants. So the prefactors will be C. Sometimes I will say what they depend on, but we will not in general have explicit bounds of those. Okay, so, and this epsilon mixing is related to this conjecture by my colleague Alberto Bressan on the cost of rearranging a set. This conjecture is still open, and as far as I know, he still has a small monetary price. This is for the students on his website who solve it. Okay. It has the following, okay. So let's call phi the flow at time 1 of a sufficiently regular vector U. And the conjecture says that if the image on the phi of a set A is mixed up to scale epsilon, then you have to pay a price in terms of the vector field U that pushes around this set. And the price is that the L1 norm in time of the L1 norm in space of the gradient of U needs to be large. How large? Over the logarithm complex. Okay. So this is the conjecture. So as epsilon goes to 0, you see that this explodes, but explodes logarithmically. And this conjecture is still open. However, if you replace the L1 norm with the LP norm, the reason why he was interested in the L1 norm is because of some other conjectures on compactness of spaces at the level of L1. So that's why there is an L1 here. But if you replace it with LP for P strictly greater than 1, then in fact this conjecture is proved. And he uses some deep geometric measure theory argument, which are in the work of Gianluca Crippa and Camillo De Lelis, on quantitative estimate for so-called regular Lagrangian flows. So I do not want to write down the precise definition of regular Lagrangian flows. How much more time do I have, by the way? Okay, perfect, yes. So I do not want to write down the precise definition, but let me just say that a Lagrangian flows is a irregular Lagrangian flow is a flows where the trajectory exists almost everywhere, and the flow does not compress too much. Okay, so your enemy is concentration here, so that the trajectory can deviate, but there cannot be too much compression. And if that's the case, then you have an estimate on the separation of the trajectory, but it's an integrated estimate. So the L1 in time, well, so this is pointwise in time. So the LP norm of the gradient of U controls pointwise in time how exponentially fast the trajectory can separate, okay, but in an integrated way. Let me say that the reason why P1 is problem here, to prove this when you put the 1 here, okay, so there are several reasons, but one is that this estimate is derived using a maximal function argument. You know, maximal function and the 1 don't mix very well, okay, pun intended. So that's one reason why it's very hard to put P1. Okay. Oops. Oh. What did I do? Okay. Let's see. Okay, so so let me say that this looks like a complicated expression, but in some sense this is to be expected. So it's difficult to prove it, but in some sense this is to be expected. So you have to work with the level sets of the flow. But it is expected because if you are in the classical Cauchy theory, then in fact you have this estimate, so the separation of the flow line is in fact almost exponential, but it's a pointwise estimate, not infinite. Okay. And let me just say that incompressible flows with sublow regularity are regular Lagrangian. Okay, so we can apply all of this. And so using the cost of rearranging set, you can study mixing rates. Okay. So by mixing rate, I mean how fast the mixing scale decays in time and whether you have perfect mixing in finite or infinite time. And all of this clearly depends on you, on the back of the effective velocity, but possibly also on the initial condition. Okay? And so the two estimates, this Cauchy-Lipschitz estimate and the regular Lagrangian estimate here, both of them indicates that what controls the behavior of the flow is the LP norm of the domain. So our mixing rate will be obtained by imposing constraint on the LP norm of the gradient of the velocity. So we will distinguish three cases. So although the two estimates, although this estimate uses the L1 norm in time, the Cauchy-Lipschitz estimate is a uniform in time. Well, I mean, here you can put uniform in time, so I will just write them as uniform in time estimate, not L1 in time. So we distinguish three cases. U is uniformly in time in WSP for S less than 1, equal 1, and S greater than 1. Okay, so, and the behavior will be very different in these three cases here. So S equal 1 in some sense is a threshold for what happens. So these three cases also have a physical meaning in some sense. So you can think that that corresponds to practical situation in which you impose physical constraint on the fluid flow. So in case A, for example, you can take S equal to 0, and that includes the case where you're constraining the energy in the flow. So the energy, the kinetic energy here, it's simply the L2 norm squares of the velocity. The case B, S equal 1, includes the case of entropy constrained flows. So what is entropy? Entropy is the L2 norm square of the vorticity. The vorticity is the curl of the velocity, and we measure the swirling in the fluid. And because we are in the torus, in fact, the entropy equal the L2 norm square of the gradient. And so it's the H1 norm of the velocity field. So case A will include L2 constraint, case B will include H1 constraint, and case C will include what we call palistrophy constraint. So palistrophy means entropy twice in Greek. And so the palistrophy is basically the entropy of the entropy. So in other words, is the L2 norm square of the gradient of the vorticity. And so these three cases have physical meaning for the optimum. Now, the optimal rates are known in all three cases now, but in case C, which in some sense is the hardest, so it's clear that the higher the number of derivatives that you control of the flow, the more difficult it is to mix, right? Because you have higher constraint that you have to satisfy. And so for a while, case C was not known, but now it is known, but you have to use both deterministic and stochastic flows. So if you only use deterministic, we can do A and B. In order to go to higher regularity, the examples that are known are, well, except for very, very, very recent results, are stochastic. Okay, so randomness helps here. If you use randomness in the flow, it helps, and that in some sense makes sense because we are looking at the correlation of the Dresden field. So if you introduce randomness, it's clear that you are helping the correlation in some sense. So we will focus the discussion just dedicate on the functional scale, but in at least one proof, which I will recall. In fact, you're working with the geometric scale, but remember that they go to 0 at similar rates. And at first, we just did numerics, okay? And so in the work with Charlie and Jean-Luc before did the case A and B before, then we looked at the case C. And they support the following. Okay, in case A, you have finite time perfect mixing. In case B, you have exponential infinite time mixing. In case C, you also have exponential infinite time mixing. So the two pictures here shows you some numerics. So you see the different line corresponds to different negative norms, and in fact, the straight horizontal line here just the alpha norm, which is monitored in the simulation because it should be constant. Right? So you can see that it's a straight line. This is a time to log plot, right? So if you see a straight line, that means exponential decay. And in the picture B, this is case B. And this picture here is case C. So this corresponds to palentropy constrained flow, and this corresponds to entropy constrained flow. And you see that for entropy constrained flow, especially for the H-1 line, which is the solid line, really looks like a beautiful straight line. Right? So this really looks like exponential. For palentropy, it's not exactly the straight line, but I have to say that it's harder to mix for palentropy. So this would just be a transient behavior. We haven't gone far enough in the simulation, and in fact, indeed, this is still successful. So we would like to prove this. Okay. So how much more time? Okay, so I think maybe it's a good time to stop. And what I will discuss in the afternoon are examples. Well, first of all, can you rigorously prove lower bounds are consistent dynamics, and then can you provide explicit examples that achieve those? And a caveat that say, when I mean example, I mean initial conditions and divergence in the vector field. I will never claim they satisfy any fluid equation. In fact, but in principle, you can always think that the divergence in the vector field satisfy Euler and have Stokes with some crazy forcing term. But that's what I mean by really satisfying the fluids equation. So in some cases, we will be able to say that, in fact, they come from Navier-Stokes. But the example that I will present in my work construct the flow by hand, and they will not satisfy. Nevertheless, they are divergence to vector. Okay, so I will stop here and I will continue in the